So let's discuss this idea of Venturimeter, what it is used for, and what principles are applied in its uh, working. What is a working principle? Fine. Venturimeter basically is a device used to measure the flow rate of a fluid through a pipe. When we say flow rate, it could be like we can measure volume flow rate, we can measure speed, and if you know speed, obviously you can calculate volume flow rate, mass flow rate, momentum flow rate, energy flow rate, all those things. Okay, so if there is a fluid flowing through a pipe, liquid, okay, particularly liquid, if there's a liquid flowing through a pipe of varying cross section like this, fine, tell me first, if we make a hole here where the area of cross section is broad, if we make a hole in the pipe, will liquid leak out or not from that hole? Vanilla, what do you say?
Millicodes.
Usually, like in daily life, like, did you ever observe from, okay, a pipe which is carrying water, if you make a hole, usually what happens? Leaks out or not? Or you tell me the condition. You said it may leak out. When will it leak out and when will it not leak out? Tell me that condition.
So pressure outside is less
Ha,
than the
good,
pressure
good,
inside the pipe.
good. It depends on the pressure. Fine. Usually, when there is flow inside a pipe, pressure will be greater than atmospheric pressure, but good that you considered that factor also. Fine. So let's assume the pressure inside is more than atmospheric pressure, so the liquid will have a tendency to flow out. Okay. Imagine inserting a vertical tube here. Okay. Like wherever this hole is made, imagine inserting a straw there. So somewhat like this. Now, depending on the pressure of the fluid inside the pipe, inside the tube, it will rise to a certain height in this straw. Okay. Let's say it rises to this height and settles. The straw or tube has to be long enough. Okay. So depending on the pressure inside, it will rise to a certain height and settle there. Okay. You have to provide a tube which is long enough. Only then this is possible. Fine. Let this height be H1. Okay. Density of liquid, let's say it is rho. And let's say the pressure here is P1 and speed of flow here is V1. Now the open surface, okay, at the open surface, the pressure will be atmospheric pressure. Then here, the pressure will be P naught plus rho g H1. Okay. Let's assume the actual pipe in which the liquid is flowing is quite narrow. Okay. What I mean is this height H1 should be very long compared to this diameter. Okay. Assume that situation. If it is very long compared to that diameter, that means if the diameter is negligible compared to the height of liquid in that column, P1 itself can be taken as P naught plus rho g H1. So we know the pressure at the point 1, P1 is P naught plus rho g H1. Okay. So depending on the pressure there, liquid will rise to a certain height and settle. Now, where the tube is narrow, there also imagine making a hole. Now, if the pressure of the liquid inside the pipe, okay, actual pipe is more than atmospheric pressure, again here also the liquid will flow out. Okay. You imagine connecting another straw here or a tube here, vertical tube. In that vertical tube also liquid will rise to a certain height. Uh, Vanilla, based on what we discussed yesterday, tell me which pressure will be greater, P1 or P2? Where the cross section is wide or where the cross section is narrow? Where will the pressure be greater?
So P1 is greater than
P1 is greater than P2, correct. At P2, at the second point, the speed of flow will be very high. So basically what will happen? Applying Bernoulli's equation, you can see that the pressure P2 will be less than the pressure P1. Just a moment. Why is this horrible? Okay. If the pressure is less, then the height to which liquid rises at that point will also be less, obviously. So let's say it rises to a height h2 and settles there. Now see, the liquid that rises in those straws, it's a static liquid. Okay, that is why we are applying P is P naught plus rho GH. So the pressure P2 becomes P naught plus rho G H2. Now H1, H2 can be measured by us from outside. So we know H1, H2, we know areas of cross section A1, A2. So we can estimate pressures, we know the density of the fluid. So what is it that we want to find out? The rate of flow. Okay, so either this speed V1 or the speed of flow here V2 is what we want. Okay, speed, like speed of a moving fluid, ideal fluid in steady flow, can be derived using Bernoulli's equation. Okay, that's the only equation we have so far, other than equation of continuity. Okay, let's apply those equations now. First of all, we know that A1 V1 equal to A2 V2. That's first equation. Next, Bernoulli's equation. P1 plus rho G H1. Okay, let me use capital H here. Just to avoid confusion, the height you see in Bernoulli's equation is the height of the point from the reference level for gravitational potential energy. So P1 plus rho G H1 plus half rho V1 square should be equal to P2 plus rho G H2, height of that second point from the gravitational reference level, plus half rho V2 square. Now the venturimeter, if it is kept horizontal, as you see in the diagram, H1 and H2 will be equal. Those 2 points will be at the same level from the ground. Okay, actual situation will be like this. As I said, the tube should be, the tube would be quite narrow. Okay, compared to heights and all. So first point, second point, they are at the same height from the ground. Fine. Then H1, H2 equal, they'll get cancelled. P1 and P2, we know the expressions. P1 is P naught plus rho G H1. P2 is P naught plus rho G H2. P naught will get cancelled. You will be left with rho G small h1 plus half rho V1 square is equal to rho G small h2 plus half rho V2 square. Simple. Okay. Density is same everywhere. It will get cancelled. So half V2 square minus V1 square is equal to G H1 minus H2. H1 minus H2 is nothing but the difference in heights of liquid in the two straws. This level to this level. This gap is H1 minus H2. Okay, let's call it as delta H. We'll substitute that there. G times of delta H. 2 goes to that side. You get V2 square minus V1 square is equal to 2G delta H. If you remember, yesterday when we tried to derive speed of a flux, it's the same equation that we got. There we got 2GH, here we got 2G delta H. That's all. So I'm writing the expression directly. If you want V2, it will be under root. Okay, same expression as that of speed of a flux, but there it was H, here it is delta H. That's all. Divided by 1 minus A2 by A1 whole square. Simple. Okay, here A1 or A2 will not be negligible compared to A1. It will be significant. They'll have to give you that in the question. Then you can tell what is the speed of flow. And once you find out speed of flow, you can tell volume flow rate, mass flow rate, all those things. Is it clear how to find out speed of flow from this kind of apparatus?
Yes, sir.
Okay. Actual device will look like this. Okay, not the actual device, but diagram will look like this. So there will be a pipe through which the liquid is flowing. And in that pipe, if you want to measure the rate of flow, you will have to create a break in the pipe. Okay, you'll have to cut the pipe and install the venturimeter there. Based on those heights, you can predict what is the speed of flow. Okay. Now, in this case, we have derived the speed in terms of height difference. Okay, but remember that everything was derived from Bernoulli's equation only. Okay. Now, there are other types of venturimeters also. Now, consider this one. They don't show you the height of liquid. In fact, they are not open. It's not safe to allow every liquid to be open to the atmosphere. Okay. So suppose there is a venturimeter like this. There is a pressure gauge connected. It will give you readings of P1 and P2. It won't tell you H1, H2. Okay. So when I want you to derive the expression for V2 in terms of all these. Okay. Fine. So applying Bernoulli's equation, you get P1 plus rho G, write this as capital H1 plus half rho V1 square is equal to P2 plus venturimeter is kept horizontal, so the heights will get cancelled. Okay. Usually the heights will never be significantly different. Okay. That's all. So you get V2 square minus V1 square is equal to 2 times of P1 minus P2 divided by rho. Okay. And V1 is A2 V2 by A1. Take common, send it that side. Okay. What you said is correct only. V2 will be under root 2 times P2 minus P1. I'm writing it as delta P. P1 minus P2, sorry. P1 will be greater, P2 will be lesser. Okay. So P1 minus P2 divided by rho into 1 minus A2 square by A1 square. Okay. So there are different designs that are possible for a venturimeter. This is one of them. Fine. So this is another application of Bernoulli's equation. Next, Magnus effect. Any idea what Magnus effect is? Very interesting idea, concept. Okay, fine. Just a moment. Venla, do you watch cricket?
No, sir.
At least occasionally. Football?
No, sir.
Okay, fine. No problem. So it's possible, like usually what happens when you throw a ball, okay, due to gravity, it will go down. That's okay. But it will stay in the same vertical plane, right? But sometimes it's also possible to make the ball or to make the path of the ball curve mid-air. In air itself, the path will deviate. Okay. After hitting the surface, it can go to the side and all. You might have played with those bouncing balls and all. No? So spinning is after hitting ground, changing direction is possible. But in air itself, it is possible to change direction. Okay. So in football, this is called a banana kick. In cricket, also this concept is applied in swing bowling. Okay. Fast bowlers, when they bowl the ball in air itself, it will swing, not after hitting the ground. Okay. So this is a result of Magnus effect, and it can be explained using Bernoulli's principle. Fine, let's see how it works. So consider a ball like this. Assume the ball is moving forward and you are looking at it from above. Okay, the ball is moving through air. You are looking at it from above. So this is the top view of the ball. Okay, so when you see from above, let's say the ball is moving this way. Fine. If the ball is moving this way, then relative to the ball, air molecules will be flowing back like this. Okay, you can assume this is streamline flow. Relative to the ball, air molecules will be flowing like this. Okay. Now, if the ball is uniformly rough, okay, roughness is same everywhere and it's not spinning around, then most likely the speed of air molecules on one side, okay, let's call it V1, or let's consider 2 points first. One point on the left of the ball, one point on the right of the ball. You are seeing from above. Okay. So these 2 points that I have marked, call them as A and B, they are at the same height from the ground. Okay. Actual situation from the side, it will look like this. Suppose you are looking at the ball from behind. The point A is here, the point B is here. Those are the points that that you are considering. Okay. So this is the rear view from behind. They are both at the same horizontal level. Okay. So the speed of flow of air on one side, let's call it V1, and the speed of flow of air on the other side, let's call it V2. Now A and B are at the same height from the ground. Fine. So capital H1 will be equal to capital H2. Okay. Let the pressure on the left side of the ball be P1 and the pressure on the right side of the ball be P2. Now, if the airflow is similar on both sides, then the relative speed of flow, the relative speed of flow of air with respect to the ball, V1, V2 will be equal. Now, if V1 and V2 are equal, then write Bernoulli's equation P1 plus rho g H1 plus half rho V1 square is equal to P2 plus rho g capital H2 plus half rho V2 square. Heights are equal anyway. If speeds are also equal, then the pressures will be equal. If pressures are equal, what happens? The force experienced by the ball from this side due to the surrounding air will be equal to the force experienced by it from the other side, and it will go straight. Okay, the forces F1, F2 will be balanced and it will go straight. Okay. But suppose we spin this ball. Okay, I'll use the same picture. Suppose the ball is rotating as it moves forward. So from above, when you see, okay, or from behind, when you see, let's say it is rotating about this axis. So from above, if you observe, it will be rotating like this with some angular velocity omega. Okay. Now, this is a real object that we are talking about. Now, real objects, the surface will never be perfectly smooth. So the ball surface will have some roughness. So you just visualize that roughness a little bit on the surface of the ball. Now, you know how the ball is spinning. Okay, it'll be rough everywhere. I'm indicating only at some part. Okay, the ball is spinning anti-clockwise. You know air is flowing in the backward direction, ball is moving forward. So Vanilla, you tell me on which side, A or B, is the spin of the ball opposite to the flow of air? On which side is spin opposite to the flow of air? Or maybe I should say, on which side is motion of the surface opposite to the flow of air?
Right side, sir.
Right side, correct. And left side, it is in the same direction. So because of the roughness, on the right side, the ball surface is moving against air. So what will happen? Speed V2 will be less. Okay. The relative speed with which air flows, it won't be that easy for air to flow past the ball. So speed V2 will be less. On the left side, the ball surface is moving in the same direction as the flow of air. So it will be relatively easy for air to flow there. So V1 will be a greater speed. Okay. And if V1 is more than V2, then a pressure difference will arise. Fine. Due to the spin of the rough surface, a pressure difference will arise. Which speed is greater here? V1 is more than V2. Okay. If V1 is more than V2, then obviously P1 will have to be less than P2 for the equation to be balanced. Fine. So P1 less than P2, if pressures are unequal, what will happen? The forces will be unequal. Force from the left side on the ball will be less than force from the right side. See here, due to the spin of the ball, due to the motion of the ball, atmospheric pressure will get disturbed a little bit. Okay, you may be thinking that, sir, the ball is exposed to air. Should it not be atmospheric pressure on both sides? No. Okay, when air hits against something, then the pressure of air can increase. Okay, so on the left side pressure will be less, right side pressure will be more. So force from the right side will be stronger than force from the left side. As a result, what will happen? The ball will deviate this way. In the air itself, it will deviate in whichever sense it is rotating. Here, when seen from above, top view, it is rotating anti-clockwise, no? So it will deviate to the left. Okay, that is what happens in a banana kick. Okay, for the player to actually execute this, when the ball is on the ground, no, instead of kicking it exactly at the center, they will kick it slightly to the side. Okay. When they kick it slightly to the side, what effectively happens is the ball will get a velocity. It will also get an angular velocity. And when it moves through air, it will be rotating. Okay. So due to Magnus effect, basically due to Bernoulli's principle, or as a result of Bernoulli's principle, it will deviate mid-air, or through air itself, it will deviate. Okay. And this is quite significant. It's not negligible. In olden days, okay, very old, I mean, many years back actually, they even used to use this technique to steer ships moving in the sea. Okay. Ships used to have long cylindrical structure. I don't remember the name actually, but when the cylinders rotate, fine, the ship's direction changes. So this is a significant effect. And the same effect is seen in swing bowling in cricket also. Okay. You must have at least seen fast bowlers rubbing the ball against their pants. Basically, why they do that is to make one side of the ball smoother than the other side. Okay. Fast bowlers, they don't spin the ball, they don't rotate the ball, they'll release it straight. Okay. But if one side of the ball is rougher than the other side, then even without this rotation, okay, on the rougher side, air molecules won't flow that freely. So higher pressure will get generated and the ball will deviate within, I mean, mid-air. So that is what is Magnus effect, how it is used. Okay, there are many other examples also. Did you understand?
Yes, sir.
Okay, fine. So these are the basic applications which are very much part of your syllabus. But based on these applications, some very tricky questions can be asked. Okay, for example, yesterday we discussed that case of speed of efflux. Just a moment. Okay. Let's say liquid at this moment is filled up to a height h. Of course, that height will keep changing as the liquid is drained. And let's say a hole is made at the bottom and assume the opening makes an angle theta with the horizontal. Okay. As a result, what will happen? The water or liquid as it leaks out will undergo projectile motion and strike the ground at a certain distance. Okay. So no need to solve this in detail, but Vanilla, just tell me, supposing the tank is fixed, how will you derive this range? Assume all the necessary information is given and area of cross section of the hole is much less than area of cross section of the tank. How will you derive the range? Fine. So see, irrespective of the angle at which the opening is arranged, the liquid is open to atmosphere. So the speed will still be speed of efflux. So you know the speed here, initial speed. After that, it's just projectile motion. The angle should be given to you. And yeah, basic formula for range 2 ux uy divided by g. Okay, because time of flight is 2 uy by g. So that 2 factor will be there. Okay, right. Next case. It's also possible that the hole is made horizontally itself, but not at the bottommost point. Maybe somewhere here. Okay, and let's say it is a horizontal opening. So depending on where you make the hole, the water will strike the ground at some distance, assuming no air resistance and all. Okay. Let's say this height is also given to you, small h. How will you calculate this range?
So UX into
Hmm.
root 2H.
Correct. Here the liquid flows out of the tap horizontally. So you know that speed, then the range will be under u under root 2h by g, speed multiplied with the time. Okay. And as height of liquid decreases, the speed will decrease. So the range will be a variable. Okay. Have you solved this question? Where should the hole be made such that range is maximum? Like at exactly what height should you, what did you say?
H by 2.
Correct. Correct. Okay. Let's just briefly recollect that idea. The speed of flow here is under root 2g. I mean, we are applying Torricelli's equation itself, but in Torricelli's equation, the height is basically the height of the free surface from the hole. Okay, so it becomes under root 2g, capital H minus small h. That is the speed of efflux multiplied with under root 2 small h divided by g. This is the formula for range in terms of capital H and small h. Now we have to choose small h, or we have to find out small h such that range is maximum. So we'll treat small h as a variable. Okay, so we need to maximize this function. You don't have to consider the square root. If the term inside the square root is maximum, automatically the square root will also be maximum. So you need to derive the maximum value of h minus h into h. This is clearly a quadratic equation, roots being 0 and capital H. If the roots of a quadratic equation are 0 and capital H, then its critical point, okay, the maximum or the minimum, will be exactly between the roots, h by 2. That way we can, okay. Next, the takeoff of an aeroplane, okay, or it's called aerodynamic lift. This also can be explained in terms of Bernoulli's principle. Now, you know that aeroplane can take off only after attaining a sufficient speed. Okay, on the runway, it will have to attain a sufficient speed, only then it can take off. Now, if you observe the cross section of the wing of an aircraft, during takeoff, it will kind of be like this. It will be tilted downwards. Fine. So this is the side view cross section. So aircraft is moving this way. So this is the direction of motion. Fine. And air will be flowing past the wing. Okay, so if aircraft is going to the left side, relatively air will be flowing to the right side. Fine. Let's assume streamline flow itself. Now this is the cross section of the wing of the aircraft. Now, ground level may be somewhere here just before takeoff. Okay, ground level will be here. Now, compared to the height of the wing from the ground, the thickness of the wing is negligible. Okay, this will actually be in meters. This thickness will only be in centimeters. So let us ignore that thickness compared to this height. So indirectly, what I'm saying is the point just below the wing. Okay, let's say its height from the ground is capital H1. And the point just above the wing, let's say its height from the ground is capital H2, these two are almost equal. Okay, right. Now tell me, when the aircraft is moving to the left, on which side of the wing, upper side or lower side, will the pressure be higher? Or on which side is it relatively easy for air molecules to flow? Upper side or lower side?
So
Can you repeat?
the air molecules will move freely on the upper side.
Upper side, correct. Okay. So the speed of flow of air molecules, relative speed of flow of air molecules on the upper side will be greater than on the lower side. In fact, here they'll be kind of trapped. Okay. Now, where the speed is more, pressure will be less, and where the speed is less, pressure will be more, provided the heights are almost same. That is what we learned from Bernoulli's equation. So as a result, what will happen? The force acting on the lower side of the wing will be greater, okay, than force acting on the upper side of the wing. There also force will be there, but it will be weak. So as the aircraft gains more and more speed, this force difference will increase. Okay, the force from below will go on increasing. The net force in the upward, I mean, the resultant force due to the surrounding air will increase. Once the resultant force due to the surrounding air becomes more than weight of the aircraft, it will start takeoff. Okay, so they can ask questions like this also. They can give you pressure above and below, or they can give you the speeds above and below. Okay, and then area, and ask you what is the upward force or upthrust or the lift acting on the wing of the aircraft. One wing, two wings, those adjustments you'll have to make. Okay, just a moment. I'll try to find out some previous year questions. Okay. Yeah, when I'll try to solve this problem. Read the question carefully. Think of what concept is applicable. You'll have to assume air is an ideal fluid in streamline flow. Okay. Try Right. So this is an obvious application of Bernoulli's equation. We know the area of cross section here A1 and we know the area of cross section here A2. Okay, they are given as, okay, radii are given 20 mm and 1 mm. Based on that, you can get the areas. And because, see, 20 and 1, the radius ratio is 20 is to 1. Area ratio will be 400 is to 1. Okay. A1 is to A2. So it's a negligible ratio. Fine. And they have given you the speed with which the piston is pushed. So you know the speed of flow here, and you're asked to derive the speed of flow here. Right? The upper end of the container is open to atmosphere. Okay, the pressure here is P naught. Let's say the pressure here is P1 and here is P2. So tell me, how did you write equations? We know V1. V1 is given as 5 millimeter per second. How to derive V2? Did you directly apply equation of continuity?
Yes, sir.
Possible. Okay, that is fine only actually because see, there is a pressure difference in this tube. I am highlighting the one tube, that vertical tube in green. In that tube, okay, there is a pressure difference. Water is at water surface is at pressure P naught. In the horizontal column, the pressure is less than P naught. P2 will be less than P naught. Okay. Now, basically what happens due to that pressure difference, you will see liquid molecules rising up and combining with air. But airflow will happen only in this region. In this region. Okay, so you can apply equation of kinematics and get the answer directly. No problem. Sorry, what am I saying? You can apply equation of continuity and get the answer directly. Okay. Next question, just a moment.